Okay, so the next paper we will go through is called SoftMC, a flexible and practical open source infrastructure for enabling experimental DRAM studies. So if you have read papers that try to understand the errors that a DRAM shows, as the one that Minesh just presented, such tools are very, very useful because you have direct access to the device and you can basically observe what's happening without any interaction with industrial memory controllers such as those from Intel or AMD. So this was a paper presented 2 years ago at HFCA 2017. Okay, let me start with a quick executive summary. So yeah, as you should know by now, DRAM has several key challenges which people try to tackle by implementing different mechanisms both in software and hardware. So two of those important problems are reliability and performance. So one example for a quite serious reliability issue was at that time recently discovered bug called Rowhammer, which I'm assuming that you also know about. If not, I think I have a short slide describing what is Rowhammer in a high level. Is the microphone on?
Push the button.
Okay, I think I didn't. Not this one. But you can still hear me, I guess. Okay, I think, okay, now it should be much better. Yeah, so basically, in order to tackle such issues, we need to characterize, analyze, and understand DRAM, and its problems with technology node scaling. So to this end, we design and implement an infrastructure that we call SoftMC, stands for software-based memory controller, which is an FPGA-based DRAM testing infrastructure. So our goal was to make it flexible so it can enable various test routines and also easy to use. So for that purpose, we enabled a C++ API that would basically make it work on make it easy to adopt by different researchers. And we have released SoftMC as an open source tool. You can go and check it out on this address. So in this work, we used SoftMC to implement two use cases. The first one was a retention time distribution test, which is actually performed by prior work. But our goal here of doing this, of implementing this use case, was to show the basically that SoftMC was implemented properly, and basically it can using SoftMC, we can see similar trends reported by the prior work. So in some sense, with this use case, we were testing our infrastructure. And in the second use case, we use SoftMC to validate two recently proposed mechanisms on DRAM latency reduction. And actually, we showed that those two mechanisms when implemented in today's devices, don't show the expected behavior of reducing the latency, and I will talk about this more. Yeah, and so here our hope is that SoftMC will enable, or actually enables, a wide range of studies, and basically you can do you can interface the DRAM directly and implement various test cases. Even you can test things that are not defined or not possible by the specification, and I will also get to that. So this is the outline of today's talk. So let me start with some very brief DRAM background. So here on this slide you see a typical memory module which is connected to a single memory controller over the memory bus, and the memory controller is inside the CPU. And if we zoom in a little bit into like one of those chips, DRAM chips that are in the DRAM module, we see that a DRAM chip is basically organized as multiple subarrays. And a subarray shown here is basically a structure that has multiple, actually hundreds of DRAM rows. And a DRAM row is basically made of multiple or thousands of DRAM cells. And vertically, those rows or the cells are connected to sense amplifiers. And the sense amplifier is a structure that can actually read and write to a cell. So let me describe how DRAM operates with an example. So here we will try to read data out from this cell. So first, the memory controller or the CPU has to activate the row that the target cell belongs to, right? And the activate operation or the activate command when sent to the DRAM basically causes this row to be enabled, and enabling that row basically transfers the charge or shares the charge in the DRAM cells with the sense amplifiers. So note that this operation is destructive. So when like doing this charge sharing, you lose the data or you lose the charge that is stored in the DRAM cells. So in order to put it back there, the sense amplifiers do an operation called restoration, which is basically putting back the data back to the cells or restoring their charge back to the original level. So it is either discharged or charge state. So only after this point, the DRAM is ready to accept a read or write command. So in this example, it will be a read command, and basically with this command, we select one or several of those sense amplifiers to read from, and then the data is sent over the memory bus back to the memory controller. And then it eventually reaches your like register or whatever you want to do with that data inside the CPU. Okay, so although we have our data back, if in future we want to read data from another cell that is not in this row that is currently open, we have to first close or pre-charge the currently open row. And to do that, the memory controller issues a pre-charge command. And yeah, the operation of the pre-charge is pretty simple. It basically closes the two rows, closes the row and restores the sense amplifiers back to their default state. Okay, so now let's look at those commands in a little bit more detail. But before that, I would also want to tell you about the DRAM retention time problem. So unfortunately, when you put data to DRAM, it cannot retain that data forever, right? So as in like most CMOS devices, in DRAM also has that leakage problem. And since you actually represent data in DRAM with a very small amount of charge, that leakage causes the data to be lost. And typically, a DRAM specification targets to have or forces DRAM manufacturers to implement DRAMs such that their cells will retain data for at least 64 milliseconds. Okay, this is why the memory controller has to refresh a DRAM device, like all the cells in the DRAM device, at least every 64 milliseconds. Okay, but in reality, like each individual cell can potentially retain data for much longer than 64 milliseconds, but the worst case should be 64 according to the spec, and devices that do not comply with this requirement are basically they like shouldn't be shipped or like they shouldn't be on the market, basically, at least not sold according to that specification. Okay, so this is the retention time problem, and so if you go back to those operations or these commands that are used to read or write to the DRAM, and look at them in a little bit more detail. So here we have a DRAM cell, which here is represented as like initially charged, and the sense amplifier is on default state. So when we activate here, when we issue the activate command, what happens is this DRAM cell shares part of its charge with the sense amplifiers, right? And then the sense amplifier is restoring that charge back to the cell. So here, this process is defined not such that the cell is fully restored, but it is only restored enough to a point where it is safe to perform the read and write operations. Okay, so here basically at this point of time where we can issue a read operation, this DRAM cell is not fully restored, or it doesn't have to be fully restored, but it's restored to a point where it's safe to perform the read and write operations. Okay, and then this timing difference basically between activate and read, which the memory controller has to satisfy, we will refer to ready to access latency. And the actual value here is something like 13 nanoseconds. Okay, and then similarly, the time that has to be satisfied between an activate command and precharge command to the same bank is defined as activation latency. So those are not timings that are necessarily applied by the device, but those are timings that has to be satisfied by the memory controller. Okay, so basically this means if you have a custom memory controller, or if you have full control over the memory controller, you can easily play with those timings. Okay, so this is essentially what SoftMC enables. And yeah, I forgot to tell you about that. And there is actually another timing parameter, which is defined as precharge latency. And this is the time between the precharge and activate to the next row that you want to activate. Okay, so here, although you can play with those parameters, if you reduce them too much, that will cause some incorrect operation. For example, trying to read before a cell is restored, or before like charge sharing happens, for example, may lead to two different problems. One, you may read the incorrect data, but the correct data might be restored to the cell. So next time you activate it properly, you might be able to read the correct data. Or you may read incorrect data, and also destroy the data that's in the cell. I think it's also possible to do the other case where you read the correct data but destroy the cell. Okay, so like it leads basically to 3 different cases, I think. And similarly, if you do precharge before fully restoring a cell, this will basically this may lead to a retention error, basically, right? Because the cell is not fully restored, and at the end of 64 millisecond period, you may lose the data, because like you have to start with a like fully restored cell at the beginning of that 64 millisecond period. And similarly, issuing activate after precharge too soon also leads to problems, because there's not enough time to put the sense amplifiers back to their default state, which is again some sort of a precharge operation. Yeah, and so basically the takeaway here is that violating latencies negatively affect DRAM reliability. But if you do it in a controlled way, so if you design a mechanism such that it takes into account those problems, you can potentially still reduce latency. So there are also other factors that affect DRAM reliability and latency. One of them is temperature. If you increase temperature, DRAM cells become more leaky. They leak their charge faster. Similarly, voltage. So at reduced voltage, DRAM circuit works like much slower. Intercell interference, basically, this is like the error mechanism that is causing row hammer. Basically, a cell, when you access a cell, it interferes with the other cells in the neighborhood. Manufacturing process variation, retention time of the cells, and other such factors also affect DRAM reliability and latency. So basically, to understand all of those and improve reliability and latency of DRAM, we need to understand these problems better. And many of these factors that affect reliability and latency cannot be properly modeled. So we don't have any like analytical or like some like better model that will tell us like what will happen to DRAM if I like reduce this timing parameter, or if I increase the temperature to this point. Such models are not available, so like the best we can do today is to perform like actual studies, actual experiments on real DRAM chips. And that is not easy with current systems we have. I mean, you can guess why, right? Because basically the way we are interacting with DRAM devices on laptops or on desktop machines is basically through the ISA, which only implements load and store instructions. Okay, but you don't have access to lower level parameters, such as you don't have access to individual DRAM commands. Okay, so SoftMC basically enables that. It gives you the ability to issue DRAM directly, like commands like activate and read and pre-charge. So you can do things like activate and then activate again, like without any other command in between, which will, I mean, obviously lead to incorrect operation, but still you can do that. Okay, so again, if we iterate over the goals of this testing infrastructure, it was one goal was to make it flexible, so we can have the ability to test any DRAM operation, and also ability to test any combination of DRAM operations and define custom timing parameters. Our goal was also to make it easy to use, such that it is like it has a simple interface and also requires minimal programming effort and time, so it can be accessible to a wide range of users. So this is how one instance of the infrastructure looks like. So basically, let's start from here. We have a heat chamber which isolates a DRAM module that is here from the outside world. So we have a heater inside the same heat chamber, which is controlled by this temperature controller. So we can like test DRAM at specific temperature, and the FPGA that the DRAM module is plugged to is also connected to a host machine, and the host machine is basically where we control the tests, where we implement the tests, and then record the errors. Or like do whatever else with the data that we read from the DRAM. So here in this instance, we implemented SoftMC using an FPGA called Xilinx ML605, and here we also use a C++ based API again. So SoftMC has three main components. One of them is the API, and then the PCIe driver, which allows us to communicate with the host machine, and then obviously the SoftMC hardware, which is implemented in the FPGA. So I'll go over those components one by one quickly. So this is how it would like to write data to DRAM using SoftMC API. So I won't go into too much detail, but here basically we have structures that generate commands, DRAM commands. So here, for example, for this activate command, we can pass directly the bank ID and row ID of the bank and row we want to activate, and then this generates the appropriate command to send to the FPGA. And then after this activate, we can define some time in terms of cycles to wait. So here we are trying to model TRCD because we are going to perform the write operation after activate. So basically, it is like pretty simple, right? So it's pretty straightforward. It is exactly what I described in the background part. We have direct access to those DRAM commands. And I will tell you more about how exactly those commands are executed in the next few slides. Okay, so here, this is where the execution actually starts. So here, by generating those commands, we don't start the execution right away, because that may lead to some undeterministic latencies between those commands, right? So we want them to be issued to the DRAM device with very specific timings. So here it is TRCD, for example. Okay, so we don't want more or less. We want exact that specific timing in order to test properly. Okay, so the next thing, I will not go into detail for this one, but basically we are using a a driver or an IP core called RIFA. This is also publicly available to communicate with the FPGA device. So you can read about this more if you're interested. Here's the reference for that paper. Okay, and also let me show you here a picture that describes how the SoftMC hardware works. So here we have a bunch of components. So the PCIe controller, which communicates with the host machine. Here we have something called instruction receiver and instruction queue. This will basically buffer and dispatch the instructions sent by the host machine together with the instruction dispatcher. And the DDR5 is a fixed block that is implemented in the FPGA. The reason why it's fixed is it has to communicate with some like specific physical interface with the DRAM, and it has to be fast. And here we have some other module called read capture that we use to basically get the data from the DRAM and send it back to the host machine. Okay, so I will show here an example of three instructions. So they will, I think, activate, wait, and read. Okay, so first in the host machine we define those instructions and then send them to the SoftMC hardware where they are getting buffered until the last instruction in this instruction sequence is received. So we do that in order to eliminate any latency that is here on the pad because of the PCIe controller or the PCIe interface. Okay, so we make sure that we have everything in the test routine downloaded to the FPGA. And after that, the dispatcher starts like dispatching those instructions every cycle. So here in this example, let's assume the first instruction we get is an activate. So instruction dispatcher is basically emitting a command, a DRAM command, the activate command to the DRAM as a result of that instruction. And then the next instruction we get is wait. So here it basically gets some custom cycles, number of cycles to wait. In this case, that should correspond to ready to access latency. And for that, the instruction dispatcher is not doing anything other than just waiting for exactly that many cycles. And then finally, we get a read command for which the dispatcher generates a DRAM read command, and then the DRAM will send data back through the read capture module all the way back to the host machine through the PCIe. Okay, so one advantage of having this in like such modular way is that you can take this design and just apply it to, let's say, a newer generation of DRAM. So this was designed for DDR3, so you can take it and make some small changes in this interface and then use it with DDR4 devices, for example. There are also some other modules that deal with lower level issues, such as like calibrating the signals, the data signals between the DDR5 and the DRAM, and also we implement auto refresh in the FPGA, so we don't have to deal with the refresh commands on this in the software. This is just like to make the life of the programmer easier. Okay, any questions so far? Yeah. Yeah, so here one limitation is that the length of the instruction sequence should be like not too large, such that it fits into this instruction queue.
And what is the maximum frequency in which we can check? Because DDR5 should also have some frequency limitation. Like we can run at some specific frequencies, cannot go beyond.
Yeah, so that is typically restricted by the FPGA. So DDR3, I think, can get to, like, I think something close to over 2,000 million transfers per second, but usually FPGAs cannot communicate with DRAM modules that fast. So here that is not limitation of SoftMC, but it's just limitation of the FPGA. Okay, but so in this instance, I think we were running the FPGA at 400 megahertz. the DRAM was working at 400 megahertz. Yeah. And the PCIe actually was not bottleneck. So it was like reading data fast enough to basically not cause any bottlenecks. Okay. And now let me talk about the two use cases we implemented. So let's start with the retention time distribution study. So here's how such a test routine looks like. So first we write data, reference data to a row, and this can be done using only like 12 lines of code using the SoftMC API. So I think those slides are shared. You can take a look at this later if you're interested. And after writing to a row, we have to wait for some refresh interval. So this can be like something from milliseconds to seconds. So here we don't use any special instruction for this, but just rely on system level functions to sleep or like wait for a specific amount of time, and then read back the data and then check for errors. And repeat this by increasing the refresh interval, so we can have a good look how much or how many cells can retain data for how long. And this entire test routine can be re-implemented with approximately 100 lines of code. So this is a plot showing the results we got from 3 different modules. So on the x-axis we have different refresh intervals, and on the y-axis we have number of bytes that has at least one error. And then this test was done at 20 degrees, so room temperature. Okay, yeah, so here we have 3 different modules, and then as you can see, so the default refresh rate was 64 milliseconds, right? But here in those experiments, we saw that with refresh interval of like 1 second, most of the cells are good. And this is something that was also observed by prior work. Only very few cells fail at even 1 second. Okay, and as you keep increasing these refresh intervals, more and more cells start to fail. I think it is not plotted here, but we also looked at how this distribution change when we increase the temperature, and that is also in line with what is reported in the prior work. So basically, this study validates the correctness of our infrastructure. Okay, the next use case is more interesting. It looks at the key idea of those 2 works. So their key idea is to reduce the latency when you read or write to cells that you know to be highly charged. So remember that 64 milliseconds refresh interval, right? So at the beginning of that 64 millisecond, you would expect a cell to be fully charged, right? So it has a very high amount of charge. But going through the end of that interval, the cell will have just enough charge to operate correctly, right? So this means basically, if you know that cell is at that point, you can potentially access it much faster because you have more charge, and then charge sharing can happen faster. And let me show you here exactly what you can save. So if you know that the cell is fully charged, as depicted here, and okay, so this is explaining what I just described. And so you can basically reduce this ready-to-access latency. And the reason is that you have more charge to share with the sense amplifier, okay, compared to the case where the cell is here at this point, where it has like part of the charge has been leaked. Yeah, and since this ready-to-access latency is a part of the activation latency here, as shown, it also reduces the activate to pre-charge latency. Okay, so you can reduce 2 different timing parameters using this technique. So using SoftMC, we wanted to look at whether this is correct, basically, whether it holds on current devices we have. And this is the test we implemented. So again, we write some reference data to a row or part of the row, and waits for some interval. So here, if you wait long, you will let the charge to leak more. If you wait less, the cell will have more charge. And this is like one of the major parameters that we play with, that we sweep in this experiment. And then we read back. So here, when we read back, we use custom ready-to-access latency parameter, because what we expect is, if you have waited shorter here, where the cell will have high charge, you should be able to read with some reduced latency and still get the correct data, right? This is what we expect. And then the next step of the test is to check for errors, and then repeat this test with different wait intervals and also different ready-to-access latency parameters. Okay, and then this can be implemented with about 150 lines of code. So what we expect as an outcome from this experiment is something like this. So here on the x-axis, we again plot the refresh interval and the number of bytes with at least one error on the y-axis. And each curve here represents different ready-to-access latency from 6 cycles to 3 cycles. So in this case, 6 cycles was the default. And we would expect something like this, right? So when the refresh interval is very, very high, where like a cell leaks most of its charge, we shouldn't be able to read correctly with any of those parameters here, right? So here, as you see, even with 6 cycles ready-to-access latency, we have some very low error rate. And if it is smaller, then we have much higher error rate. But somewhere at this point, where we wait for a very short amount of time and then try to access the cell again, we should be able to recover the correct data with latency lower than the default, right? But if you look at our experimental results, we see something like this. So here, the left-hand side is somewhat what we would expect, right? So I mean, apparently with 3 cycles is very low. So no matter how soon you read the cell, you still get an error. So you can avoid that. So basically here, you are destroying the data no matter what. So it's even if a cell is fully charged, it's not possible to read it correctly with such a small latency. But it seems like with all the rest of the latencies, we can recover the data or read the data without any errors. But what happens later is that those curves somewhat overlap, right? So we don't see the behavior that we see here, where the lines are or the curves are separated from each other, right? So basically, this is not showing the expected behavior of being able to read with low latency when a cell is highly charged. Yeah, so this is what I said. So our hypothesis about why we do not observe the expected effect is that although we can control each individual DRAM parameter, there are also some timings that are embedded in the DRAM chip, right, that we do not have control over. Okay, so those are just some fixed latencies inside the DRAM chip. And here's an example of such fixed latency. So here, this is representing, so on the x-axis we have time, and here we have the charge that is on the DRAM cell, and also the charge level that is that the sense amplifier has, right? So at the beginning here, it is at pre-charge state, so it's somewhere in the middle between high and low, and the cell has some amount of charge here. So with the activate command, we will start the charge sharing process, right? And at some point, after the charge sharing completes, the sense amplifiers are getting enabled, so they start restoring the value that they sensed from the cell back to the cell, right? So basically, this is one of the fixed latencies that we have in DRAM. So there's no way with the current interface to play with this timing over here. But what we can play with is this ready-to-access latency. Okay, so we can change the position of this dot over here, but we cannot change where this happens exactly. Okay, so this is fixed. And this might be a reason where we basically lose most of the potential of this idea, so we cannot observe the expected behavior even if you have high amount of charge to start with, since you have to wait until this point, even though you are ready maybe to like complete charge sharing at this point, you cannot exploit it because you cannot play with this timing parameter. Okay, is that clear? I hope so. Okay. Yeah, and so I presented you two ideas that SoftMC enables, and I will talk you about. I'll tell you about some future directions that SoftMC can enable. So first, it can enable more characterization of DRAM, specifically how cell characteristic change with different generation of technology nodes. So you know that like manufacturers are always trying to reduce their transistor and capacitor size, so they can like fit more data, or like they can make their devices denser, so we have like higher capacity memories. And another study to perform would be to answer this question, basically, what types of usage accelerate aging. So like, for example, is it causing like the DRAM to age faster if you operate at high voltage? So you know that like some people do overclocking, so they put their CPUs or DRAMs to operate at higher voltage and high frequency. So is this like causing the DRAM to accelerate faster, or to age faster or slower? This is a bit different, but SoftMC can also potentially enable characterization of non-volatile memories. So there are like plans, or actually it's an actual product right now that by Intel, which uses the DDR4 interface to actually pack some non-volatile memories in the same type of module. Oh my God, what was the name? Optane DIMM. So it is a product right now that I think Intel started shipping to some companies, but not individual users, I think. But yeah, I didn't check recently. So basically, potentially, you can use the SoftMC to basically change, to do some changes and also experiment with non-volatile memories. And it can possibly be extended to support different memory scheduling policies. So you can possibly experiment like and see like what reliability issues different memory scheduling policies may cause, or potentially you can even do some performance studies if you can like emulate the system you want to model properly using SoftMC. And yeah, you can use this also to do some like workload analysis, especially for workloads that can tolerate some sort of errors, you know, so you can do that kind of stuff. And potentially you can also use it as a testbed for in-memory computation. Okay, and this is basically pretty much about this. So let me quickly conclude. So SoftMC is the first publicly available FPGA-based DRAM testing infrastructure, and it's flexible and easy to use. And we demonstrated it using two use cases. One of them was retention time distribution study to validate our infrastructure, and then second, we showed that the key idea of two recently proposed mechanisms on DRAM latency reduction are not actually working with the DRAM devices we have today. And yeah, so we here argue that SoftMC can enable many other studies, ideas, and methodologies to improve memory systems going further. And again, here's a link to our GitHub repo with the FPGA code, and also like the drivers and other stuff that you will need to run SoftMC. Okay. Any questions on this? No? Okay.